Good afternoon, everyone, and very nice to see all of you here. I actually had not expected to see so many people here, so you're giving me the nerves here, especially when we've got such a wide audience as well. But it's good to see all of you here, and I hope the next 20 minutes or so when we explore lithium battery chemistries that you'll find it interesting. I've been over at the stand, at the PowerPlus Energy stand just down there, and it's been quite interesting over the last 24 hours just listening to some of the questions that people have been asking me about lithium batteries, because I think there's a lot of lack of knowledge perhaps in the industry about the different battery chemistries. So hopefully by the end of this session we'll have something more that you can take away from here. It's interesting that the original title of this talk, I'm not sure who dreamt it up, but it's called Various Lithium Chemistries and Quality Variations. I've actually changed the title because I think it's probably better said that it's selecting the best lithium battery chemistry for your ESS projects. So what I want to do is to look at the practical side of lithium chemistries and have something that you can walk away with and that you can apply into your projects. There will be opportunities for you to ask questions as well at the end, so hopefully I won't run over time this afternoon. Just a little bit about myself. I graduated from the University of Western Australia back in 1985. So I've got 34 years of electrical engineering experience in electrical, electronics and software. I've done some systems engineering stuff as well. Throughout my entire career, I've been developing products for different people. I've done some stuff in healthcare. These smart bands that people wear, that's the sort of stuff that I've worked on. I've done some work on telecommunications. Mobile FTPOS, the company that I worked for in the year 2000 was the first to introduce mobile FTPOS systems, which are very common nowadays. Control systems, autonomous mining vehicles. I have had several patent applications and I've got one granted. And so in 2015 I was given the title of Digital Disruptor from the Australian Computer Society. So hopefully I'll have some interesting information to share with you. So since the year 2015 I've been looking at renewable energy, and as you all know there's already a lot of people working on things in harvesting of renewable energy, solar, wind and all that sort of stuff. There's a lot of people working on improving the efficiency of systems so that renewable energy can go further. There's a lot of people working on inverters, chargers and things like that. So I've decided that what I want to do is to focus on storage. More specifically, I wanted to focus on commercial and industrial storage because I think if there's a way in which we can make it easier for companies to store their energy, especially in a form factor that allows for scalability and modularity, I think that's a winner for everyone. So I've put some of the products that we've recently released, but these are products that can be used not just in commercial and industrial applications, they can also be used in residential applications as well. And the next thing that I would like to move on to after I get all these storage systems working the way that I want is to look at how to manage that, to optimize it, to go with the loads that we present to the system. Now, the people have asked me why on earth did I actually change my career direction to move towards renewable energy. Well, in the year 1999, my wife and myself, we bought a house with a large north-facing roof. We deliberately chose that house because we wanted a large area that we can use for solar panels. Now, at that time in 99, when we wanted to install solar panels, we actually had to get council approval to put a solar panel system up. That's how long ago it was. They said, oh, you're going to change the whole facade of your house by sticking all these black things onto your roof. But that was in 99. We also bought a house with a large basement. It was a disused wine cellar. My dream at that time was to put in lead acid storage. I thought, well, I needed a place that I can easily plumb air in and out. I wanted somewhere cool to store the batteries. And so I said to my wife, I really like this house, let's buy it because I want to be able to put batteries there. Now, it was because I wanted to do something for my children and my grandkids that I decided that, that I wanted to put in all this energy management and storage sort of stuff. But eventually, it was only in the year 2010, it's good over 10 years that we installed solar PV, and I was still an early adopter. I paid $15,000 for a 5 kilowatt system. Nowadays, you can get solar systems of that size for a lot less. I started seriously looking for solar storage systems in the year 2015. I turned 50 in 2014, and for my birthday present, my wife and the kids bought me tickets to Las Vegas to go to the Consumer Electronics Show in 2015. So in January, I packed my bags and went to Las Vegas, and it was there that I began to find people who sold and were interested in lithium batteries. At that time, they were still fairly new, and I wanted to learn about how I could apply lithium battery technologies into today's world. And so I started working closely with Chinese cell manufacturers from various parts of China, and also working with universities in Australia to try and get some traction to build these products. So now in 2019, I'm the technical director at PowerPlus Energy. What we do is we design and manufacture our lithium batteries in Victoria, in Melbourne, just outside Melbourne City. So the question that we always ask is, are lead-acid batteries passé? Have we come to the end of lead-acid batteries? Well, lead-acid, as you know, have been around for a long time, since the turn of the last century, the 20th century, started in the 20th century. And they have provided robust energy storage and power delivery for a long time. Because of their relatively low cost, they've been a really good way of just storing energy relatively cheaply. And you're guaranteed a really good long life if you treat them well. But what do we mean by treating them well? If you keep them relatively cool, below 35 degrees C, and if you over-engineer it. Now on that curve there, you will see that in order to achieve, say, 1,200 cycles of life, you really need to run the batteries with a depth of discharge of 30%, which means you have to significantly over-engineer your system to be able to store a lot of energy. And when you've got long strings of cells in a large system, it becomes very unmodular. I had a friend who's currently down in Mundribilla Roadhouse trying to solve a problem with a large lead-acid system that was installed down there. He's got a bunch of cells that have failed because of temperature variations across the string. You can't just repair a couple of batteries in the middle of a lead-acid string, and that's where the beauty of lithium comes in. Now, as you probably know, lithium batteries have been around for a while. It's not a new kid on the block. In 1980, there was a guy, Professor John Goodenough, who invented the first rechargeable lithium-ion cell. That's quite a long time ago. 1980 is going to be 2020 next year. That's 40 years ago, effectively. But it took Sony 11 years to commercialize that technology and start introducing that battery into electronic products. And that technology is based on lithium cobalt oxide. And here's a little bit of information about lithium cobalt oxide. Basically, it's a 3.6 volt lithium chemistry. So what it means is if you need to achieve 14.4 volts, you put 4 cells in series and so on. The energy density of this particular chemistry is very high. It's between 150 to 250 watt hours per kilogram. And they're still used today in your telephones, in all your high energy need products, in your portable devices. And they will give you between 500 to 1,000 cycles of usable life, cycle being full charge to full discharge. And so they're good for smartphones or tablets and all that sort of stuff. But there is a catch. With high energy density, there's the possibility of thermal runaway if your charging and discharging currents exceed certain thresholds. And of course, when you hit 150 degrees, they actually have a thermal runaway problem. And they will ignite, and we've seen the effect of that in some things like remember the Samsung Note 7, which was not that long ago. And because of all that, we've got all this aviation battery problems. You can no longer carry batteries on planes and all that sort of stuff, all because of batteries like this. But not all lithium batteries are problematic. The lithium cobalt oxide is particularly bad because of the high energy and power density. Because one small fault in your battery will lead to a big mess, as happened on the Samsung Note 7. 30 to 50 watt hours per kilogram is what you typically get out of a lead acid battery. For lithium cobalt oxide, it's 8 times that. That's 150 to 250 watt hours per kilogram. Or if you look at it in real numbers, for the Samsung Note 7 battery, that's 55 gram battery provides you with enough capacity for 3,500 milliamp hours. Now, if you can imagine doing that with a lead acid battery for your phone, you have to add the weight of a loaf of bread to your phone in order to be able to power that phone. So that's the beauty of lightweight lithium chemistries. Now, what other lithium chemistries are available today? Now, because when people talk about lithium batteries, they don't realize lithium is actually just a generic term, right? So I've taken the liberty of taking information out from the Battery University. They've done a lot of useful work. There's a link there, and I'm sure you'll be able to get to that link when you get the download of these slides. So no point trying to write that, it'll take you too long to type it all in or to write it all out. But just to run through it quickly, because I want to get to the chemistry that's of interest to us today. Lithium cobalt oxide, we've already mentioned, is one chemistry. There's lithium manganese oxide, lithium nickel cobalt manganese oxide, a bit of a mouthful. People call that the NCM or NMC chemistry, which is what you find in a lot of electric vehicles, some of the LG Chem batteries that you see in their power systems. Lithium ferro or lithium iron phosphate, or called LFP, and then there's lithium nickel cobalt aluminium oxide, shortened to NCA, and then there's lithium titanate. Now that graph there tells you a comparison between the energy densities that's available from the different chemistries. As you can see, the NCA is extremely energy dense, but it may not necessarily be power dense. So what it means is you can store a lot of energy, but you still need a lot of cells in order to be able to deliver power. So you always have to have this trade-off between energy density and power density. And recently, I was down at Monash University in Melbourne, and we caught up with the researchers there with their lithium sulfur battery. Now, they believe that is going to be the next low-cost battery that will be available on the horizon soon. Now, but what's the catch with all of these batteries? Well, the lithium sulfur battery, the cell voltage is about 1.85 volts, which means in order to achieve 48 volts, you will have to have a large number of cells. And in order to achieve the sort of battery, you need a very sophisticated electronic battery management system in order to be able to flatten the characteristics of that battery for ease of use. So therefore, what you find today is that there are only some lithium chemistries that are suitable for the sort of work that you and I are involved in. And you already know that, these chemistries. The NCM battery, which is available in the LG Chems and also in the electric vehicles. As I said before, they're typically lightweight and they've got a fairly high energy density. And the other one, which is more of my favorite, is the lithium ferrophosphate or the LFP cylinder cells. They've got good storage density, but more importantly, they're robust. They can handle high temperatures and can be used in a lot of applications. I won't stay on these slides for very long. As I say, you will be able to get the same information when you get the downloads for these later on, but I'll just flash them up quickly. These are the two main chemistries that I want to focus on today. Now, I don't know how many of you know about the way that cylinder cells are made, but cylinder cells are numbered using this particular nomenclature. An 18650 cell refers to the fact that it's got an 18 millimeter diameter and a 65 millimeter cell length. And then you've got the 26650, which 26 millimeters diameter, 65 millimeters length, and 32700, which is a bigger version, a bigger brother version again. So these cylinder cells are only 3 of the more common sizes, but for electric vehicles, you've got the 21700s and other types of sizes that will fit better into a vehicle. And in order to be able to use those batteries effectively, you have to put them into a pack. So here is an example of a pack of cells which are connected in series parallel to be able to give you the voltage and the current, the capacity to be able to deliver the power that you need. And you see on the front of that pack, on the side of the battery pack, a little red circuit board. That red circuit board is a battery management system. It protects the cells it protects the cells against abuse, but also it keeps the cells in good health. Prismatic cells, these are the sort of cells that you see in your electric vehicles, energy storage systems for home use, and so on. Pouch cells are also used in electric vehicles and home storage system. And again, you see the battery management system circuit board on the side of the battery there. Now, lead acid, we talked about lead acid a few moments ago. These are the sort of discharge characteristics of a lead acid battery. The lead acid battery discharge tends to be highly affected by the amount of current that you draw and the time frame within which you draw that current. So the more quickly you need to draw current, the more poorly the lead acid battery performs. And the discharge rate tends to be designed to be used in the tens of hours rather than in the tens of minutes. On the other hand, lithium batteries have got a fairly flat sort of a discharge curve. As you can see, they're very bundled together regardless of the discharge current that you put through them. And the interesting thing with the lithium nickel cobalt manganese cell is that the voltage difference between a cell that's fully charged and a fully flat cell is quite high. So you've got 4.2 volts at the top and 2.5 volts at the bottom. So you've got a 1.7 volt difference between fully charged and fully discharged. The lithium ferrophosphate, on the other hand, has a much flatter characteristic, which is why I like to use them in my designs. And you will see that from top to bottom, you've got 3.6 volts down to 2.5 volts. There's only a 1.1 volt per cell difference. So if you've got 16 cells in series, you're not talking about huge voltage changes. And so your inverter and your chargers don't have to work particularly hard to keep everybody happy. Now, lithium ferrophosphate cells, because they're not as energy dense as the NCM cousins, they're suitable for stationary energy storage applications. And they're suitable as lead acid replacement for these reasons. There's a operating voltage compatibility. So you can get a 12.8 volt lithium ferrophosphate cell to match with a 12 volt lead acid, 25.6 volt lithium to go with a 24 volt lead acid, and so on. They've got very stable output characteristics, and the existing lead acid chargers can be tweaked or taught to actually charge a lithium battery. You basically remove the absorption and the equalization stages in your charging from the lead acid charging algorithm, and then you'll be able to charge your lithium batteries, the lithium ferrophosphate batteries, pretty much directly. And if they're managed well, these cells will deliver 10,000 cycles or more, charge-discharge cycles, over the life of the battery. And that's why you need a battery management system to make sure that everything will work. The lithium ferrophosphate cells will work over a dynamic range, temperature dynamic range from 0 to 65 degrees C. That's at the cell level. So that's a very wide temperature range, unlike a lead acid. There's no ventilation required, and they're extremely efficient. So for every milliamp hour that you put in, you can get 0.94 milliamp hours back out. So 94% of what you put in comes back out, which is significantly better than what you get with a lead acid battery. So in order to maximize your lithium-ion battery life, what you have to avoid is elevated operating temperatures. And that's the same for any battery chemistry, because once a battery is running at a high temperature, you run the risk that the battery will be over-exercising its chemistries. So that applies to lead acid, lithium ion, or nickel metal hydride cells. The daily temperature variations is not a real problem for lithium because it's got a wide temperature range that it will operate over. But what you have to do is manage temperature variations between cells connected in series. What you don't want is cell on this side, going to this side, there's a temperature gradient, because what you end up with is an unevenly charged battery pack. And you also have to try to avoid overcharging and over-discharging them to stop them from being damaged. Poor connections at some of the key junction points can sometimes cause overheating, and so the local cell overheating can cause that cell to be damaged as well. So this is why you need battery management systems, right? What the battery management system what it does for you is that it will stop overcharging, it will stop over-discharging, it will manage the current flow so that it won't overcharge, it will manage any short circuits so that to protect it against fire. It will stop any overheating. So if the cells get too warm, it will shut down the battery. And also it will carry out cell balancing and matching. As cells over a period of time will degrade, and there will be some variations between one cell to the next. So it's important that electronically you try to optimize the amount of energy that's stored in the battery pack so that you get the maximum out of that particular battery pack. You can have a choice of analog BMSs, or you can have a choice of digitally controlled BMS. Your battery management system is really your insurance policy for a very expensive asset. I brought along with me one of the battery management boards that I designed recently for our batteries. This is a 120 volt lithium battery management system. It's been designed to be particularly thin in this direction to be able to fit into a 2 rack unit rack mount case. So basically what we've done is we've taken the equivalent of a car battery management system and squished it into 3 circuit boards this size. It took a lot of mucking around, but we eventually managed to do it. So you can come over and talk to me and I'll show you the battery into which these boards have been deployed. So these are all 100% Australian designed and running 100% Australian software. We've got customers in America who have specifically asked that they buy our batteries because they don't want to have any foreign software running inside. They want to know where the software has come from. Okay, just before we go, just some helpful hints. Lithium batteries cannot typically be connected in series without external battery management systems. Things like this will allow you to connect batteries in series. This particular sequence of boards, you can keep adding to the end of this. You can cascade these, and it will allow you to control up to 1,000 volts of lithium batteries in series. And unmatched batteries can become a real problem in poor capacity performance. I'll just quickly skip through. You know how I talked about cells with different temperatures? I went to a factory in China because as part of my job to go to visit Chinese factories to do due diligence. This particular battery system was offered to us, and I took up my thermal camera, and they said, "What are you doing?" I said, "Well, I want to see how your battery performs thermally." They said, "Oh, we've never done that before." So we discovered that from top to bottom, there's a 7-degree temperature difference between the top pack and the bottom pack. So as a result of that, the top pack has about 3% more capacity than the bottom one. So what you end up with is an unbalanced system waiting to have problems down the track. So it's so important to manage heat in a thermally sensitive environment like lithium batteries. So what we've done is we've actually put the packs into a much tighter, compact arrangement so that any temperature variations are very limited across the pack so that the cells don't suffer from poor cell capacity balance from one side of the pack to the other. So in conclusion, lithium batteries offer significant advantages, and these are the advantages that we've already talked about. And careful system design is absolutely necessary if you want a quick return on investment, and most importantly, you need safety. Ease of maintenance is also important. Have a chat afterwards if you want to talk to me. I'll be at the stand till about 4:30 today. My email address there, if you can't grab me, you can drop me a message, or you can message me on the Smart Energy Conference app if you're using that, or you can find me on LinkedIn as well. So thank you very much.